In this video, we're going to do an example of projectile motion. So we have a ball that's being thrown southward into the air. We have a mass of 0.8 kilograms for the ball. The speed of the ball at which the ball has been thrown initially is 30 meters per second, and it forms an angle of 30 degrees to the south. Excuse me, 30 degrees with the ground. We threw it in the southern direction. A west wind applies a force of 4 newtons to the ball all the time, and it's pushing it to the east. It asks where the ball lands and with what speed. All right, so we're throwing the ball due south. When we think about the standard orientation of the XY plane, due south is straight down negative Y direction. So the Y component of our initial velocity would be 30 cosine of 30 degrees times J, except that we're going in the southern direction, so we need a negative in front of that. The rest of it's going upwards, so we have a 30 sine of 30 degrees times K. That simplifies to negative 15 root 3J plus 15K. We're told that the wind applies a force of 4 newtons. Well, force is mass times acceleration. So to get acceleration, we need to divide that force by the mass. So the acceleration in the X direction, the positive X direction, since it's going easterly, will be 4 divided by 0.8 times I, and then acceleration to gravity to pull it down back towards the ground, the negative 9.8 K. All right, so anti-differentiating, 4 divided by 0.8 gives you 5. Take an antiderivative, we get 5t times I, and then a minus 9.8 t times k, plus whatever the initial velocity is. Well, that's what the velocity is at time 0, and we have that as negative 15 root 3j plus 15k. Plugging those pieces into our velocity function, and then anti-differentiating again. Here we get 5 has t squared times I, minus 15 root 3 times tj, and then a plus 15t minus 4.9t squared times the k, plus the initial condition. We're throwing the ball from ground level into the air, so the initial position will be the 0 vector. So this is now our position function of the ball. The ball is going to hit the ground when the y coordinate, the z component is 0. Setting that equal to 0, we get 2 time values. The first time value, of course, corresponds to when we initially threw it. The second time value is when it comes back down and hits the ground. Plugging 150 over 49 in for t and approximating, this will give you your vector for when it hits, where it hits the ground. And then plugging that 150 over 49 back into your velocity up here and taking its magnitude gives you a speed of approximately 33.7 meters per second.